In this video tutorial, we will continue our lesson on the quantum model of the atom. Specifically, we will be looking at electron characteristics and their atomic orbitals. In part 1 of our video tutorial, we briefly introduced the concept of wave-particle duality, how very small particles like electrons or photons can have properties of both waves and particles. But when we say an electron has wave-like properties, we aren't referring to a physical wave. Instead, we're talking about a probability wave. By collecting data on the position of the electron, with enough data points we start to see a pattern forming, where we are most likely to find the electron. In these blank areas, we are unlikely to find the electron, so the probability of finding it is pretty low. But in the darkened areas, that's where we're most likely to find the electron, so the probability of finding it is very high. When we map the position of the electron inside the atom, we start to see this. In the nucleus of the atom, electrons are not supposed to exist, so there's a very low probability of finding an electron. But as you get further away from the nucleus, the probability of finding an electron approaches 0, again, because now you're in an area where it's an unstable orbital. And that's why we see a little blank area here where the electron is unlikely to be found. Until you get to the next energy level, and that's where you're most likely to find the electron again, with a high peak, high probability. And then, of course, the further away from that orbital you get, the less and less likely you're able to find the electron. If you look at this atom with 3 shells, again, same thing. In the nucleus, unlikely to find the electron. But as you approach or get further away from the electron, within the first shell, now you have a high probability of finding the electron. But then you get to an area where the electron is not allowed to be. All right, this orbital is not stable. Again, it drops to, or approaches 0 anyway, probability of finding the electron, until you reach the second energy level, where it is a stable wavelength. And so then at that point, you increase the probability of finding the electron, until once again, the further away you get from the second energy level, until you approach 0, where you're unlikely to find the electron again, until you get to the last energy level, the third shell over here, where the wavelength is stable, and again, you find a high probability of finding the electron. And then from there, the further away from the nucleus you get, the less and less likely you are to find that electron. Now, the reason why we're so focused on the idea of probability is because Werner Heisenberg discovered that the position and the momentum of an electron cannot be measured with a high certainty at the same time. So what that means is, if I know where the electron is, I can't know where it's going with a high degree of certainty. Vice versa. If I know exactly where it's going, I can't know where it is exactly. The more you know about one, the less you know about the other. This is one of the fundamental laws of quantum mechanics. The very act of measuring a small system changes the system itself. To better understand why that is, let's look at microscopes. We use them to help us see very small objects. So with a light microscope, light rays will come in, bounce off the object we're trying to look at, and then through a series of lenses end up being magnified so we can see it with our eyes. But look at how big these wavelengths are. Look at all the details not reflected back to our eye. So of course, with a light microscope, there is a limit to how much you can magnify the object. Anything that's too small in between these wavelengths comes out blurry, so we lose resolution. To increase our resolution, we use an electron microscope, but instead of firing light to bounce off our object, we're firing electrons, and electrons have a much smaller wavelength. And because electrons have a much smaller wavelength, the wavelength in between what is being missed is a lot smaller as well. And this gives us better resolution, so we can start to see pieces that otherwise would have been missed if it was using visible light. So here we're trying to see a super small object using super small objects. That would be like trying to find a bowling pin by throwing a bowling ball. Let's pretend we have a very dark bowling alley. I want to know where the bowling pin is located, but the only way I can do that is by throwing a bowling ball. I know that the bowling pin is unlikely to be here, very close to where I start off. I know the bowling pin is very unlikely to be behind the wall back here. The bowling pin is most likely somewhere here, most probable. Now, the moment the bowling ball hits the pin, I know exactly where the pin was, but now I don't know what its momentum is. Where is it going? In which direction? The very act of measuring this system has changed the system. And that is the basis behind the Heisenberg uncertainty principle. As such, we can only predict the probability of an electron's position or movement at any given point. All right, so we can't actually predict where the electron will be at any given point in time, but we can predict with a great certainty where we're likely to find the electron. We do this by recording the position of an electron over time. And if you record the position of an electron over time, you start to see fuzzy patterns or a cloudy shape form. This is the region of space around a nucleus in which we are most likely to find the electron. And we call this an electron cloud at this point because it's not a hard defined shape where the electron must be here. It's a cloudy fuzzy area where we're most likely to find the electron 90% of the time. And then out here, it's not impossible for the electron to be out here, it's just improbable for the electron to be out here. Now, Erwin Schrodinger was able to come up with an equation to describe the behavior of an electron in three-dimensional space. All right? Now, just like y equals mx plus b requires two coordinates to solve and describe the position and properties of a line, Schrodinger's equation requires 4 quantum numbers to describe a specific volume of space where an electron is likely to be found. Thankfully, you won't have to use Schrodinger's equation this year, but if you're planning on taking chemistry in university or college, you'll probably have to use a portion of it at some point. For now, let's just concentrate on what these 4 quantum numbers represent. So the 4 quantum numbers are n, L, we pronounce as m sub L, and m sub S. Each electron in an atom has its own unique 4 quantum numbers. When we take those 4 quantum numbers and plug them into Schrodinger's equation, we're able to describe the properties for that electron. Alright, so this is going to be one of those topics where it won't make sense until we actually do a sample question. So I'm going to go over what the 4 quantum numbers represent. You probably will still be quite confused, and that's fine. But once we do a sample question, it should make a lot more sense so that when I go back to the slide, now that you've got context, it should be a little easier to understand. Alright, so let's use an analogy to help us understand the 4 quantum numbers. Alright, let's pretend you own a drone delivery service and your customer wants you to drop off their lunch right on their bed. They are too lazy to get out of bed, they're too lazy to go down the stairs to the lobby to pick it up. No, they want the drone to fly through their window and drop the food right on their laps while they're lying in bed. So, how will you do this? How will you direct the drone to your customer? Well, you need to know their location. So the first step would be to identify what floor are they living on. So are they on the 3rd floor? Are they on the 6th floor? On the 9th floor? Which floor are they on? Well, that's what the principal quantum number is. All right, the principal quantum number, n, is essentially describing which orbital energy level and the size of the orbital energy level for that particular electron. Where is it currently? Is it in the first shell? Is it in the second shell? Or is it in the 3rd shell? Etc., etc. Now, just like in a condo, the higher up you go, the more expensive those units typically are going to be, with the most expensive unit being the penthouse units at the very top, whereas the units at the very bottom tend to be lower in rent, lower in cost. Similarly, the further away you are from the nucleus, the higher the energy level, the more energetic the electron is going to be. So the higher up in the condo you live, the higher the rent, while the further away you are from the nucleus, the more energetic the electron is going to be. Now, in all likelihood, in grades 9, 10, and 11, your science teacher probably simplified the truth for you, and they told you the first shell holds only 2 electrons, the second shell can hold a maximum of 8 electrons, the third shell can hold a maximum of 8 electrons, and so on and so forth. But that's not entirely true. This version of the truth is only going to work for the first 20 elements of the periodic table, and that's why we stopped asking you to draw Bohr-Rutherford diagrams after calcium. In reality, yes, the first shell does hold a maximum of 2 electrons, and yes, the second shell holds a maximum of 8 electrons. But once you get to the third shell, you can actually hold a maximum of 18 electrons, while the fourth shell can hold a maximum of 32 electrons. This is known as the 2n squared rule, where n represents the energy level. So in the first energy level, 1 squared is 1, 1 times 2 is 2, it can hold 2 electrons. In the second energy level, 2 squared is 4, 4 times 2 is 8 electrons can be held there. In the third energy level, 3 squared is 9, 9 times 2 is 18. In the fourth energy level, 4 squared is 16, 16 times 2 is 32, etc., etc. So in grades 9, 10, 11, we didn't want to bog you down in the quantum mechanical model of the atom, so we gave you a simplified version of the truth, where you could only hold 2 electrons in the first shell and 8 electrons in every subsequent one past that point. And then we just avoided any other atoms past calcium, so we didn't have to worry about the 2n squared rule. You'll find introductory science courses do this quite often, especially when we're dealing with conceptually difficult topics. We just don't want to confuse our students early on. In any case, just keep in mind that the maximum number of electrons that can be found at each energy level is 2n squared. So after I found out which floor they're on, I need to identify which unit they are in. Is it one of the bigger units on the floor with 2 bedrooms, or is it one of the smaller bachelor units with only 1 bedroom? And that's what the second quantum number L describes. It describes the orbital shape, or from our analogy, describes the condo unit that they live in. So for instance, an S unit would be a simple unit, one with only 1 bedroom, whereas a P, D, or F, premium, deluxe, or fancy units, would have multiple bedrooms, or they'd be corner rooms with nice views of the area. So with electrons, instead of a simple premium, deluxe, or fancy condo unit, we have sublevels labeled S, P, D, F. S stands for sharp, so this is a sharp suborbital shape. P stands for principal, and these are the principal suborbital shapes. D stands for diffuse, and these are the diffuse suborbital shapes. And F stands for fundamental, and these are the fundamental suborbital shapes. It's important to note that 2 electrons on the same sublevel have the same energy, while electrons on different sublevels have different energies. So let's go back to our condo analogy. Take a look at condo unit number 5 and condo unit number 6. They're pretty much identical to each other. Same furniture, same furnishings, even the same view because they're on the same level. Well, you would expect whoever's living in condo unit number 5 and whoever's living in condo unit number 6 should be paying the same amount of rent. Well, similarly, these 2 electrons, green and blue, are both on the same energy level, second floor, second energy level, and the same suborbital, a p suborbital. They're just orbiting in different orientations. Green is restricted to the x-axis, while blue is restricted to the z-axis. But these 2 electrons are considered to have the same amount of energy. However, condo unit number 3 and condo unit number 6 will not have the same rent. Number 3 is more expensive than number 6 because this one only has 1 bedroom, whereas this one has at least 2 bedrooms and a lot more square footage. So even though they're on the same floor, the same level, they are not the same units. They're not the same sub-level. Thus, they won't have the same price or the same energy. So an electron on the 2s would not have the same energy as an electron in the 2p. All right? So even though they're both on the second energy level, number 2 and number 2, because this is a s suborbital, while this is a p suborbital, the p suborbital is going to have more energy than the s suborbital. All right, so all electrons in 2p have the same energy, but an electron in 2p does not have the same energy as an electron in 2s. All right, so we've identified what floor the person is on. We've also identified what unit they're in. Now we have to identify what room they are in. So you'll notice the higher end condo units have a lot more bedrooms than the lower end condo units. Similarly, s orbitals only have 1 shape, a spherical shape. P orbitals have 3 suborbital shapes, one along the x-axis, one along the y-axis, and the one on the z-axis, all of which are dumbbell or figure 8 shaped. D orbitals have 5 suborbital shapes, and F orbitals have 7 suborbital shapes. So that would be like saying simple condo units only have 1 bedroom, while the s orbitals only have 1 suborbital shape. Meanwhile, premium condo units have 3 bedrooms, while the p orbitals have 3 suborbital shapes along the px axis, py, and pz. Deluxe or fancy condos have 5 bedrooms. D orbitals or diffuse orbitals have 5 suborbital shapes. And finally, the fancy condos have 7 bedrooms, while the fundamental f orbitals have 7 suborbital shapes. Now it's important to keep in mind that each orbital, or suborbital rather, holds a maximum of 2 electrons. So that's why on the second shell, s orbitals only hold 2 maximum. That would be like saying each bedroom only sleeps 2 people. So 2 in this bedroom and 2 in this bedroom for a total of 4 people in this condo. So if this p orbital has 3 suborbital shapes with 2 electrons per each, then that means this condo altogether has 3 bedrooms, 2 people in each bedroom, or in this case 2 electrons per suborbital for a maximum of 6 electrons allowed in p orbitals. And since d orbitals have 5 suborbital shapes with 2 electrons for each, 2, 4, 6, 8, 10, d orbitals can hold a maximum of 10 electrons. Same with the f orbitals. There are 7 different suborbitals, so 2 each, 2, 4, 6, 8, 10, 12, 14, for a maximum of 14 electrons allowed in the f orbital. Now another thing I want to mention is that generally you don't find the fanciest condo units on the ground floor. The fanciest units, like the penthouse, are typically found on the top floor. Well, similarly, you won't find the f fundamental orbitals on the first energy level. Instead, the first energy level only has one orbital type, s. Once you get to the second floor, the second energy level, you now have 2 orbital types, s and p. On the third level, you'll have 3 types, s, p, d, and on the fourth level, you'll have s, p, d, and f. Now be aware, the 5th energy level does have 5 orbital types, but we're not going to worry about that one because every element that we have discovered on the periodic table fits in these 4 suborbital types. If you go into theoretical chemistry or theoretical physics, then sure, we can deal with the 5th one at that point, but I'm not going to worry about it because that's beyond the scope of our course. Just remember, the higher up the unit is, and the more fancier it is, the more expensive it will be. Similarly, electrons become more energetic the higher up you go in the shell number, and of course the higher up you go in the suborbital value. So to recap, n is the principal quantum number, and it describes the orbital energy level and size in which the electron is currently located. L refers to the sub-level type, s, p, d, or f. But you can't just plug in s, p, d, f into Schrodinger's equation. We need numerical values. So each orbital type is given its own value. So sharp orbitals are given an L value of 0. P, or principal orbitals, are given a value of 1. D, diffuse orbital types, are given a value of 2. And F, fundamental orbital types, are given a value of 3. So if S, P, D, and F are assigned their own numerical values, then Px axis, Py axis, and Pz axis should be assigned their own numerical values as well. We refer to this as a third quantum number, m sub L. This is the magnetic quantum number. So in our analogy, we describe this as which bedroom in the unit the person is located in. Now, unfortunately, your textbook does a pretty bad job of describing how this all works, but essentially, Px is given a value of -1, Py, value of 0, Pz, a value of +1. If you recall, d orbitals have 5 suborbital types. The middle one is always labeled with a 0. To the left are -1 and -2, while to the right are +1 and +2. But which one of these is 0? Which one of these is -1? Which one's -2? The answer is, I don't know. It is past my pay grade. Someone next year in university with a PhD can explain that to you at that point. The only one I care about are these ones, Px, Py, and Pz, have a value of -1, 0, and +1. For d orbitals and f orbitals, I'm not particularly concerned about which m sub L value relates to which one, because I'm never going to ask you to draw these anyway. You will be asked to draw Px and Py and Pz. I think that's within your abilities, but drawing these shapes or these shapes, I really don't want to be marking this. So we'll say matching m sub L values to the proper diagrams for d orbitals and f orbitals is outside the scope of our course, but matching them for the p orbitals is fair game. That being said, you still need to know how to label them. So f orbitals have 7 suborbital types. So 1, 2, 3, 4, 5, 6, 7. The center one is always assigned an m sub L value of 0, while the ones to the left are given values of -1, -2, and -3, and the ones on the right are given values of +1, +2, and +3. Again, I don't know which one is given a -1, which one is a +3. Doesn't matter. Just know that -1 is one of these guys, +2 is one of these guys, and it is irrelevant for this course. So let's put everything we've learned so far together and try to get the first 3 quantum numbers for this specific electron. Since it's in the second energy level, its n value, the principal quantum number, will be 2. It's in a p orbital, and those have an L value of 1. And finally, it's in the px suborbital, so therefore its m sub L value is a -1. Please don't forget the sign, which is -1. If you put a 1 there instead of a +1, if you give me half of an answer, I can only give you half of a mark. So make sure you include the sign. Don't just leave it as a 1. All right, let's try another example. I would like you to press pause and come up with the first 3 quantum numbers for this specific electron here. All right, so press pause. When you're ready, press play, and we'll go over it together. All right, so this electron is in the third energy shell, so its principal quantum number will be 3. Its L value is going to be a 0 because s orbitals have an L value of 0. So I'm going to put a 0 here. Now, if you recall, s orbitals only have one suborbital type, and the one in the middle is always going to be a 0 since this one has no other options. 0 is going to be it by default. All right. Now, if it was a p orbital, the center one would be 0. To the left would have been -1. To the right would have been +1. If it was a d orbital, 0 would be the center, -1 to the left, -2 to the left, +1 and +2 to the right. But since s orbitals have nothing to the left or to the right, the center must be 0, so there's no other option. We're going to say 0. Alrighty, so these are the first 3 quantum numbers for this specific electron. Alright, so the final number we're dealing with is the 4th quantum number. This is known as the spin quantum number, denoted with the symbol m sub s. It can have 2 possible values, a positive half representing a clockwise or up spin, and a negative half that represents a counterclockwise or down spin. If you recall, each suborbital holds a maximum of 2 electrons. So to minimize the amount of repulsion between electrons, one must have a clockwise spin, while the other one has a counterclockwise spin, and that's denoted by a pointing up or pointing down. Alright, so let's put it all together now. What I want you to do is press pause, and then try and give me the 4 quantum numbers for this specific electron right here. When you're ready, press play, and we'll go through it together. Alright, so this electron is in the 3rd shell, so its energy level is 3. Next, it's a d orbital, and if you recall, d orbitals have an L value of a 2, so we'll write down a 2. Now in terms of m sub L, d orbitals have 5 suborbital shapes, and the middle one's always a 0. To the left is -1, -2, to the right is +1, +2. Since the electron is in the -2 suborbital, we can write down -2. Finally, its m sub s value has 2 options, positive half for clockwise or up spin, and negative half for counterclockwise down spin. Since this electron is pointing down, it's going to be a negative half. Alrighty, so that's how we identify the 4 quantum numbers for any electron in an atom. And once you have the 4 quantum numbers for a specific electron, you can then plug it into Schrodinger's equation, which will allow you to predict the properties and characteristics for that specific electron.